Hello, my friends. Dr. Mohamed Nezami here with another lecture. Today, we're going to continue talking about SIW devices, design and modeling using ANSYS HFS system. Now, again, I have I'm an independent consultant for RF and microwave circuit designs. I do passive and active components. I operate out of the Middle East area in Jordan. You can call me on this number, or you can email me if you have any cooperation opportunity that I could help you with, especially for those of you who are from small design companies. I work with you closely, very flexibly, and very reasonably on rate, since I operate out of the US, makes things much cheaper. Okay, so today we're going to talk about bandpass filters using substrate integrated waveguides. And the previous video, I introduced SIWs in a simple, practical, quick review. So now we're going to go in and try to see the design of bandpass filters, just the most common class of those filters. I know there's variety of them, but we're going to look at a few particular ones, and the ones that I'm going to look at are exactly the same as if you they mimic waveguide filters. They're basically made of irises and posts within the waveguide. So just to refresh your memory, what is an SIW? SIW is basically a transmission line that is made to mimic waveguides, except the height is the height of the substrate. There is no B height to it, so it's integratable, low profile, and all that. This is a picture of how it is. Basically, you got a copper piece up, bottom and top, and you just stitch. You make VFs on both sides, and these dimensions in here, which are the center to center distances, which is A in this case, and then the center to center via placement P, and then the diameter of the via. Those basically, along with something we call the effective A, which means this is similar to the case with microstrip lines, where the width becomes an effective width to account for the fringing capacitance. This here is basically what we would use to make the SIW exactly a waveguide in the TE10 mode. And there are some formulas made, constraints for design. The wavelength is basically here giving, so pretty simple equations to build one of these transmission lines or waveguides. Now, to integrate these to a microstrip line, we introduced last time, we said that we've got a 50 ohm line, which is in this case this, and what we do to get to the SIW, since this is much wider, so it's much lower impedance in here than 50 ohm, we use tapered lines to get with, in this case, the width is, the second width is width2, and the length is L2. And what this would be basically is an impedance transformer that transforms 50 ohm microstrip line with this width here to the SIW. And likewise, we do use one at the output. And we introduced the equations for the second impedance looking into the SIW is giving here, and we gave the references to that. Of course, Z1 is the impedance on this line, and this is a pictorial copy of how this thing is constructed on a BC board. Oh, let's scroll too much. Okay. The second thing that we're going to talk about, introduce here, is basically just like a waveguide. This, we have a cutoff frequency for the lowest mode, TE10, and then the TE20. And these are the equations in here. And basically the operating bandwidth of this guide is basically somewhere between these two. And that is this here, okay? That's where the first thing you would want to do when you're designing a device using SIW technology is you want to make sure that you're within the bandwidth, otherwise you excite higher order modes, okay? So the effective width is given by this equation, okay, which is also being introduced. So today we're going to talk, one of the filters that I'm going to talk about is a filter that is similar to this, and this is again from the open literature publications. So basically you got an SIW with a bunch of irises, and these irises, the width of these irises and the distance, that's the lengths in here, which is length 1, length 2, length 3, length 4, length 5. And so these are basically with the distances between the opening, the iris width in here. These are the way we design these. We come up with these based on the frequency synthesis tools, which I'm gonna not go into, but you start out with filter shape, and then you decide the topology, Chebyshev versus Butterworth, and so on, and then you come up with the polynomial coefficients, and those gets transferred into these. And this filter very much acts just like a waveguide filter using the this structure where you have a bunch of irises in the middle. And this is how it looks like when you fab it, okay? Now, there are two other type of filters. One of them is the post filter that is like this, okay? Similar to the waveguide, is exactly parallel to it. And then this one here, which is basically building these sideways stubs or metal pieces on the inside. So having said this, let's go in to HFSS and start looking at these. I've got a few, two of these filters, one at KA SATCOM band and one at KU SATCOM band. But let's start with a refresher here. If we have a waveguide, and in this case, this waveguide is happened to be a WR75, which is basically WR75, you may recall, is a KU band 1, and it's 750 mil wide with 375 mil height. And so what I'm going to do is I'm going to run this, okay? And I want to observe the higher order mode and the lower order mode. The TE10 starts at M1 and Mach1 here, which is about 8 gigahertz on continuous. That's the cutoff frequency for TE10. TE20 basically starts out at 16 gig and above. So just so that I refresh your mind. So now, if you want to operate, if you want to build anything at low frequencies in here, say from 8 gigahertz to the 15 gigahertz, you want to make sure that that is with the safety margin. That's where you would want to place the usable bandwidth of the lowest order mode. Otherwise, you have to go and excite the waveguide with the TE20, and that's pretty complex and unusual to do that. But you just want to make sure that you stay away from or you redesign the waveguide components so that the TE20 mode is pushed further up in frequency. So now one thing to do is how do we observe the cutoff of these modes? We look at the propagation constant, basically that's the gamma. So that's another way of seeing how that happens. Okay, like in this case, this is the imaginary part. So the imaginary part is always 0 until you start propagating the mode, okay? So let's look at the E field now and just observe how the TE10 mode and the TE20 mode propagates. So this is, for instance, this is the, let's animate this. This is the TE10 mode, and this is at frequency 18 gigahertz. And let's just go back and show okay. So if we look at, well, let's get rid of this also. Now, so we've got the frequencies, okay? We've got, for instance, in this case, this is right now at 18 gigahertz. 18 gigahertz, as you can see in here, you're really into the area where both modes can propagate. So let's go ahead and go back to the 10 gigahertz. And then we're going to see that that is basically this mode alone. And right now, I'm not exciting the waveguide with this mode, but I'll show you in a minute. So this is all just to review. If we go 4 gigahertz, of course, we don't propagate. So let's go back to, let's say, 10 gigahertz right now. And let's go and excite it with, let's go to the fields and excite the TE10 mode and kill the TE10 mode. And you can see right away that that is basically what we have here. Okay. Modify the plot. So at so we can see that this is the okay, let me just make sure I've got this configured right. So we got field. It is so, oh no, I'm sorry. I didn't look like a TE20. Okay, so there we go. This is the TE20 mode, and as you can see, it is propagating because it's past the cutoff frequency. So now what you want to make sure, that's basically a demonstration that the mode, you have to keep track of your modes so that when you design your devices, you don't end up losing a lot of power being transposed to the other modes. So let's, now we can do the same thing to the WR28, but let's just go ahead to the filters. And this is the first filter, and this is in the KU band. So basically what we have here, we have a basically the substrate, and then we have the vias are shown in here. So you can see that these are the SIW vias, and these are the three. These are the you can see here's 1, 2, 3, 4, 5, 6 irises in this case. Okay, and we have the impedance matching sections to the SIW wave, and on the bottom we have the ground. So, and these are basically two ends of metal where the I inserted the excited the waves and then the wave ports. So now let's look at the response of this. Here is the response. You can see that this is from 9.9 all the way to 11.34. The return loss still needs a little improvement on this side that can be optimized. So what we have here, we have the filter dimensions and all parameterized like in here. And so we can run optimization on this or tuning on this. We can sweep the parameters or run optometry on this and get this to do better job in here. So let's go back and look again on the E field, how it behaves. So this is, let's see what we have, just to make sure that we are exciting this with the TE10 mode. We got the, oh, it's a single mode anyway. So now, just to, this is right now is running at 17 gigahertz. Okay, so we want to run into the middle of the band. So we run it at M3, which is in this case at 10 gigahertz. So, okay. 10 gigahertz. So now let's animate this and just show you the propagation of the E field in the filter from input to output, and you can see the hot areas where the resonances are. These are the cavities in here. So you can see that the wave comes in, spread into the substrate, and then all of a sudden, as soon as it hits the via walls, it squeezes in and it passes along all of these things. So where now, if you excite it with something that is below the pass band, say in this case 5 gigahertz, look what happens. So basically the signal comes in and it just can't pass through, keeps bouncing back and forth onto the excited port. So this is basically one of these filters, just for the joy of looking at this again. Now let's look at another. So this is this filter. So now we can go back and look at the substrate itself without the irises, just to show. This is the KU band. Okay, so we've got this guy here. This is the same filter, except I removed the irises from it, just to look at the waveguide, the SIW alone. And so the frequency response of this, okay, so here it is. So we have a frequency response. So you can see this is the TE20 mode, and this is the TE10 mode. And the way I did this is basically you come into the excitation port, and in here, you tell it how many modes you want to run, okay? And if you want to view how the field distribution onto these ports, you could come into the port field display and just go in, for instance, on one and zoom into this, and you can see the E lines in here, where if you go to the second mode, which is TE1020, you can see where that is. The distributions are a little different, okay? All right, so let's close this and let's take a look at another filter. This time it's a KA band one, and that's this guy here. And this guy this time is, there are less V's. This one here is, let's see, I got the V's are not. Just trying to make it more transparent so you can see it. Okay, so we've got, these are the irises. We've got 1, 2, 3, 4, 5 cavities. Okay. And the response of this filter, this is the response of this filter. So we got this filter is from M1, which is 21.9 gigahertz to 24 gigahertz. Okay. So if you want to view the E field again, so okay, here we go. This is this, and if you want to animate it again, we can animate this. I don't know what frequency this is right now, so let's go back and check this. It must be about within the passband. So that, yeah, that's 23 gigahertz, okay? So you can see 23 gigahertz passes beautifully in there with the intensity of the field within the cavities is shown. Where if you go, let's see, 18 gigahertz, which is below, as you can see here, you can't make it. All right, so let's just go back and refresh ourselves to let's go to the Ka band, the WR28 waveguide. Okay, and what are the WR28, the dimensions basically, for those of you might recall, there's like 280 mils by 140 mils. So it's a tiny little waveguide for millimeter stuff. But let's look again at the frequency response of this. So this is excited, and so this is what we get. As you remember, this one has the TE2O mode doesn't start until like 40 gigahertz. So you're okay from 20 plus gigahertz all the way to like 38 gigahertz. Huge bandwidth with this one because it's tiny dimensions. And so let's just demonstrate. This is the E field. And let's just animate this for a moment, just for fun. Okay, so we can see that this right here is at 45 gigahertz. Okay, that's past the TE2O. So let me back it a little bit into the 32 gigahertz. So this is 32 gigahertz, okay? TE10 mode, okay? Now, if I were to come in and say, let me see if what happened at if I try to excite a TE2O mode with this, and so let's see if we can do that right here. So we're gonna zero this and make this one, and okay this, and as you can see, we really can't propagate the TE2O mode. So just to verify also. Now, so what we can do is we can modify this so that we can go to the higher frequencies, and we know that 45 gigahertz is well within the and you can see the double TE2O E field distribution in there. So now, what about exciting both modes? That can happen. So let's go again and just set it up so that we can see that we got both. And that's what you got. So you got a mix of both modes propagating in there, and now it's a mess. So just to show you, just for fun. So again, just to review, we have looked at two SIW filters, okay? The filter is basically made of, this is the SIW piece, okay? And with a bunch of irises, these irises, the distance between them and the opening, the width of the opening in here, is basically the parameters that are needed, that you need to find out in dimensions initially. And this may involve using another package like ADS or some other filter synthesis program, because this, you might remember from filter theory, you start out with the filter shape, the shape, frequency response shape, and then you go on to implementing that in a transfer function, and that transfer function then again gives you a bunch of G's, we call them G0, all the way to whatever polynomial length that you have for Chebyshev or Bessel or these other classes of filters. And those G's, there's ways to transform, basically it's beyond the scope of this session right now to go through it, but You can go into lots of papers online and in the IEEE literature that basically shows you how to do this. So, well, there you have it again. Basically, we have shown basically the SIW filters. So I hope you enjoyed this. We're going to go on next to the rest of the lectures, as I promised, where we're going to cover a few more filters, cavity resonators, cavity coaxial resonators. We're going to cover waveguide filters as well. And then we're going to go into radial combiners. Okay. And then OMTs. Okay. Orthogonal transducer. And so plus other stuff. So check my website listing down below and share it with your friends. Thank you very much. Appreciate it. Thank you.